Okay ไมโครโฟนหาย image image segmentation. Okay, this is more advanced now. Okay, image segmentation. Segmentation is basically the process to subdivide an image into constituent region. Okay, we call it objects. Okay, subdivided into two parts. Okay, the object, which is the things of interest, and the rest are called the background. Okay, so basically we want to divide an image into objects and background. Okay, it's a mid-level. Okay, it's a mid-level image processing because the input is the image, the output is some attribute of the objects now. Okay, which is different from image enhancement or image registration. Okay, because those are the low level. Okay, because input is image, output is another image. Okay, so this is more advanced. Okay, the thing is you want to segment out the object of interest. There are three different approaches. Okay, the first approach is called continuity-based approach. Okay, basically is to find anywhere in the image that there is an abrupt change of the intensity. Okay, so basically this continuity means where there is a change, okay, it should separate the image. So basically it's the pipe detector, the line detector, and the edge detector. The second approach is called similarity-based. Okay, similarity-based means it uses group of regions. Okay, this is more like, you know, if you learn statistical modeling. Okay, they can use like decision tree or any other things. Okay, to group the data. Okay, that has similar features. Okay, in this case, usually we use the intensities. Okay, but not necessarily intensity. Okay, it could be anything as long as they are similar. They're supposed to be grouped to each other. Okay, so the group of regions that has similar predefined criteria. Okay, and methods are like the simplest one is tertiary. Okay, we have learned tertiary. Okay, and we're gonna learn region growing, region merging, and splitting. And the last approach is hybrid. That means it uses both age and regions. Okay, use both of them together. Okay, the hybrid approach that we can be learning is watershed method. Okay, watershed method. Okay, I guess since this one has 2 lectures to cover, today we're just gonna cover half of it. Okay, and after the midterm, we're gonna cover at the other half. Okay, so we don't need to go too fast, apparently. Okay, next is detecting the discontinuity. Okay, basically, discontinuity can be features that is prominent. Okay, so we can use this as features. Okay, for example, you could use pipe processing, line processing, lie detector, or edge detector. Okay, actually there's one more that usually used, but I haven't put it in here. It's called Harris corner detector. Okay, it can be used too. Okay, you use to find the corner of the object as well. Okay, but it's just not in this book. Okay, if you want to present as the project at the end, okay, you might want to find a paper on corner detector and then present it to your friends. Okay, all right. Usually, all these discontinuities are most of the time is local. Okay, so basically you need to do something else after that, called the edge linking. Okay, you might want to do edge linking to find the boundary of the objects. Okay, the difference between the word edge and boundary is that the edge can be fractions. Okay, can be just a small part of the boundary that is not connected. Okay, but somehow you need an algorithm to connect all these edges together. Okay, to become the boundary of the object. Okay, this is a little bit higher level. Okay, and it can be done locally. Okay, local processing, or it can be done globally. Okay, that means it can be done through the whole image. Okay, if it's local processing, you do connect the edge through windows. Okay. For the global processing that we can be learning is half transform. Okay, you need to know half transform. Okay. All right. Yeah. Okay. So, are you ready? Okay. This is the overview of what we will be learning today. First, to detect this continuity, basically we can use the linear, the windows, right? So it's a linear filter, okay? And this is, we use a 3x3 linear filter, okay? W1, W2, W3 until W9, that's the smallest window we can get. If you want to find the isolated point, okay, you can use this mask, the A, and the surrounding is -1. What is this mask? Have you seen this one before, right? Full Laplacian, that's right, it's the full Laplacian. Okay, you can see that this one will have prominent pixels at high values of 8 up front, right? This is the second order derivative. Okay, after you apply this mask, and then you can do treachery. Okay, in this case, you're gonna find one isolated point. Okay, in this case, it's just 1 pixel. Okay, just 1 pixel. For example, here, you have this image of the wind turbine blade. Okay, by part, a turbine blade. And if you want to detect any flaw, okay, you go through the Laplacians, and you can see, well, you kind of cannot really see much, right? And you can see there's a dot here, okay? And you pass through the treachery, okay? You can see the spot that is in there. Next is the lie detector. The lie detector, we can also use this, okay? For example, the point detector, the lie detector like this, we call them template matching. Okay, template. So we use the window as a template of what we are looking for. Okay, and this template gonna go through the image. Okay, go through the image, and wherever it has high value, that means it's matched with the template, and that's how we get the result. Okay, for example, here, if you want a horizontal line, okay, you can have the template as a horizontal line like this, a 2, 2, 2, and -1, -1, -1, -1, like this. Or if you have a 45-degree line, you got the 2, 2, 2 in the diagonal, the rest are -1. Okay, and this is the vertical line, this is the -45-degree line. You can see that some of these usually sum up to 0. Okay, it's basically the first derivative, right? Okay, but in a different manner. Okay, we define it as a line. Okay, and after you pass through these filters, R1, R2, R3, R4, okay, through the image, and then you can do the treachery. Okay, you can pass through the treachery. For example, here, this is the image that has straight line. Okay, straight line like this, and then if you go through the horizontal line or vertical line, and so on. Okay, this one they go through the -45-degree line. Okay, you can see any part that is 45-degree line and matched with the filter, okay? Match the shape or the size, the same object as the filter. It will give you some high values, okay? Give you some high values. This, the one on the left here is actually grayscale, okay? It's grayscale values, okay? You can see, and then you, after this grayscale, you can pass through thresholding to make it black and white, okay? It depends on the threshold also, okay? You can set up a certain threshold. In this case, you set a very high threshold, okay? And you end up with this 45-degree line. You can see from this original one, okay, this one and this one are two horizontal 45-degree line, negative 45-degree line. But how come this line here does not appear here? It's not segmented, but it has only this one. See, the one over here. The reason being, this one is actually a 45-degree line with 1 pixel thick. Okay, it matched with the template more. This one is more than 1 pixel thick. Okay, if you see, if it's more than 1 pixel thick, you cannot really use this template. This template is only for 1 pixel thick. Okay, so it matched better with this template. Okay, so if you do thresholding, it probably disappears because it's not at the exact match. Okay, this match better. Okay, the rest are different degree, right? So you need different angles. Okay, you don't need to use but the smallest is 3x3. You can increase the size to 5x5, 7x7. Okay, if you want to detect the 2 pixel thick, you might want to increase this template. Okay, to be 5x5, and then you got the 2 and the 2 in the middle. Okay. Okay, go ahead and do this. Everyone. You actually you read the text.png. Okay. And in tools. And you're supposed to segment the letter A from the text.png. PNG is black and white. Okay, it's binary. Go ahead and do that. Okay, do you get this? In the first line, where is it? Okay. First line, we just read text.png. Okay. So this is the image that we read is binary, and the second line here we what? We crop the letter A. Okay, you crop the letter A from here. Okay, this letter A. Okay, and then we pass this letter A through the image. We use this letter A as template. Okay, we use this letter A as template, and then we pass through the image. We call it filter 2. Okay, filter 2 pass through A with the in window with the template img, or actually the pass the template A through the image img. Okay, and next you're gonna get the value of y. We normalize it to between 0 and 1. Okay, so we divide it by max of y. Okay, max of y means you make the value when you pass through a filter. If it's exact match, you can get the highest value of 1. Right? If it's not exact match, if it's similar, you have lower values, maybe 0.9, 0.8, and so on. Okay, so this one we normalize to 1, and then we even show here. Unfortunately, I could not see anything. Okay, actually you're gonna see something in here. Oh, here you see some dots up here, right? Okay, those dots are the letter A, the location of letter A. For example, here, this location of this letter A, okay, when it's tilted or when it's rotated, the letter A probably not look the same because it's not the exact match. Okay, after that we use the thresholding. So we have z more than 0.9. Then you're gonna get the binary. Okay, the binary. Then you even show. Okay, you can see that the highest values here. You're gonna find letter A at 3 different locations. Right? Can you see this? Well, you will see 3 different locations. Right? Here, 1, 2, and 3. You'll see 3 different locations, okay, which match the here. This WA, water, and rich, and that THA, tea. Okay. Over here, you can use this as a center, these 3 points as a center, and then you can go back to the image and you can segment the A. Okay, that's it. Okay, we use template matching. Okay, so in this case you can apply for anything. Okay, suppose you want to find a picture of something in the image. Okay, you got to have the image of that thing first, use it as a template. Okay, and then pass through the filters. Okay, wherever it get the highest values, that's where it can find. Okay, just imagine like playing Finding Voldo, right? Have you ever played that game? ไม่เคยได้ยิน Finding Voldo คืออะไรที่กดแล้วก็แบบกระดิ่งไม่ใช่หาคนเนี่ย Voldo ใช่ไหมหาคนอยู่ในรูปภาพถ้าเป็นสมัยเด็กๆมีรูปภาพมีซีนมากมายแล้วก็หา Voldo ว่าใครหาได้เจอก่อนคนนั้นชนะนะครับแต่ถ้าเกิดเราใช้ template matching ก็เอาเข้าฟิลเตอร์ทีเดียวได้เลยโฟโต้ก็หน้าตาเหมือนเดิมนะครับมันก็จะทีเดียวเสร็จนะครับแต่ถ้าใช้คนหาอาจจะนานแล้วถ้ามันหมุนอะไรนะthe problem is what happens if it's rotated like the letter A here is rotated 90 degrees would it detect? No, it cannot. Okay, it cannot detect. Okay, so So if you want it to be invariance to rotation, what do you need to do? You need to rotate the template, right? Okay, you need to rotate the template and then you go through. Okay. Over here, what is the Z here? Here. This is the grayscale. Okay, the grayscale. Okay, you can see this is how it tells us how similar it is. Okay, let's change the image, the threshold. Okay, let's change the threshold here from 0.9 to be lower, like 0.8. What happened if you change the threshold to 0.8? Try it. Here, if you change the threshold to 0.8, how many points do you see? ไม่เจออะไรเลยเหรอเจอเยอะเจอเยอะขึ้นใช่ไหมเอ๊ะทำไมในนี้มันไม่เจอเลยอ่ะทำไมของผมมันดูตอนนี้มันดูยากอ่ะมันดึงออกมาได้ไหมเนี่ยเจอไหมเจอเยอะขึ้นถูกไหมมันไปเจอตัวไหนบ้าง
D G
right you can see here it might see this G this letter G as an A right because it looks similar to the A or the D okay the D might look similar to the A that we have okay so it depends on the threshold also okay how similar you want it to be however this template matching is not robust to rotation, just like you say, and it's not robust to the the scaling, right? It's only fine due to the translation. If you got a bigger letter A, it probably won't see. Okay, so it got to be exact match. Okay, if you are interested, okay, in the final project, you might want to find some algorithm that they adjust from here. Okay, to be invariance to rotation, then you'll find some other features. Okay, basically you need to transform the original image to something else, and then you find some other features that's invariant to scaling and invariance to rotation. Okay, and you can find that. Okay, and present it as project as well. Okay, all right. Okay, so basically this is image template matching. Okay, let's take a look at gradients. Okay, edge detector, okay, we're gonna do the, basically is edge detector derived from the gradient, okay, or gradient which is the first derivative, or the Laplacian which is the second derivative. Okay, basic formulation is that the edge is the boundary between two regions that's relatively distinct grade levels, okay, properties. Assumption is that the edge detections, okay, assumption for edge detection is that the regions are sufficiently homogeneous, okay. That means the surrounding the edge got to be homogeneous, okay, so that the transition between the two regions can be determined by the discontinuity alone, okay. Most of the edge detection techniques, okay, has the idea based on the local derivatives. For example, here, step edge. Okay, step edge is usually very obvious because the left and the right you can see distinctively find the edge. However, most of the time it's not step edge. Okay, most of the image has ramp edge. The gray levels does not change abruptly. Okay, it has a ramp edge like this, so it has some slightly going up like this. Okay. In the case of the ramp edge, okay, here, if it's a ramp edge, if you take the first derivative, this is what you're gonna see, right? When there is the on the left, on the black one, okay, it's become 0. Along the lamp, it's non-zero, it's positive, okay? And after the ramp, it becomes 0 again, okay? This one is the first derivative. You can see that derivative of the constant black or white image is 0, okay? When there is a ramp, it becomes non-zero. Secondly, we can do the second derivative. With the second derivative, okay, and the derivative of the constant of the ramp is a constant. If you do the second derivative, in this case, in this case, you can see after you do thresholding, suppose you do thresholding like this, you're gonna get the edge points. Okay, we call it edge point, which is the pixel that's on the edge. Okay. Edge point are the pixels on the edge of the objects after thresholding. Okay. For the second derivative, you can see that the second derivative would have a positive peak at the starting of the lamp, and it has a negative peak at the end of the lamp. Okay. Over here, how can you find the edge point? Usually, we find the positive edge lamp and the negative edge lamp here. Okay, it's the middle. Okay, we do zero crossing. Okay, we draw a line from here, and then we find the value that is supposed to be 0. Okay, we call it zero crossing. Why is it called zero crossing? A lot of times we don't know, okay? It's not exactly 0. In programming, you can never, after you manipulate the values, right? You can never get 0. So basically, we search along here to here, where it changed from positive to negative, okay? Or change from negative to positive. That's where we call it the zero crossing, okay? And in this case, you're gonna find the edge point at the middle of the ramp edge. Okay? Okay, you're gonna find the edge point at the middle of the ramp edge. If you use first derivative, you're gonna have thick edge. Okay? If you want just the middle, you do zero crossing of the second derivative, you get just 1 pixel of the edge. So basically, to find for edge detector, you can apply first derivative or you could apply the second derivative. Okay, you could apply either. Here, for example, this is the image. Okay, if we have no noise at all, variance is sigma is 0. When there is no noise at all, you can distinguish the edge, first derivative or the second derivative using the zero crossing easily. Okay, you can distinguish it easily. However, if you increase the noise, okay, from 0 to 0.1, you can see the ramp edge or the first derivative of the ramp edge. If you do the thresholding, you can still do it, right? You can find the edge. Or if you do zero crossing, it still works. Okay. However, if we increase 10 more times, the noise 10 more times, you can see that over here, it starts to be blurred, okay? You cannot really find much, okay? And over here, for the second derivative, there is no way you can find the zero crossing, okay? So the edge point for the first derivative is still possible with some noise, but for the second derivative, it's almost impossible. If you increase the edge, the variance to be 10 times, then both of them fail. Okay, both first derivative and second derivative fail. So, this one we says that the first derivative is more robust to find the edge than the second derivative. Robust in this case means under some noise, right? You don't have, if you have too much noise, okay, second derivative would fail. Okay, you got some noise, first derivative can still work for up to a certain threshold. Okay. So we can see that derivative operations are very sensitive to noise. If you're going to use the first derivative or second derivative, you got to be careful for segmentation. Okay, if you want to use first or second derivative for segmentation, got to be very careful. You want to get rid of all the noise first. Okay, the better the no noise, the better you can segment the image. Okay, gradient. Okay, like I used to say, gradient is actually vector. Okay, it has gradient in x and gradient in y. A lot of times we, instead of just finding gradient in x and the gradient in y, we find the magnitude of the gradient. The magnitude of gradient is square root of fx squared plus fy squared. Okay, but this calculation can be very complicated. Okay, can be computationally expensive because you got to square them and then you got to take the square root. Okay, so if you want to implement it in hardware, a lot of times you just have absolute value of fx plus absolute value of fy. Okay, this one and this one is not different, not much different. You can try it at home. Okay. Actually, gradient, not only does it have magnitude, it can also have angle, which is defined as the arctangent of fy over fx. Okay, could be both. However, this one is actually the magnitude and the angle are both nonlinear, right? Are both nonlinear. A lot of times you want to use the linear mass, okay? And we have mentioned about it, okay? You have Robert Cost, you could have Privet, okay? Or you could have Sobel. Okay. So slightly different, okay? This is the image of the object of the building. This is the image. What's the number B? B is the absolute value of gx, component of the gradient in the x direction. Okay, if you got the gradient of x direction, you can see most of the horizontal line would appear. Okay, you are detecting the horizontal line. See here, this image, you can see most of the vertical line are prominent. Okay, if you combine the two, absolute gx plus absolute gy, this is what you get for the whole building. Okay. Any questions? Okay. However, a lot of times you might want to change it to the 45-degree line, okay? Or in this case, same sequence, but with the original image smooth. Oh, okay. So this one is without smoothing, okay? You can see here, the last one is combined horizontal and vertical. So over here, same thing. If you get rid of the noise first by the 5x5 smoothing filter, this one is the horizontal line, this is the vertical line, and this is the combined of the two. Okay. Can you compare this image on the lower left with the one in previous here, with the previous line? What do you see the difference? You see any difference? Which one looks better? With or without smoothing filter? With smoothing filter. Okay, you can see here, you can see all over on the rooftop. Okay, you see a lot of noise. Okay, actually there's a aliasing thing here happen. Okay. If you do the smoothing filter, okay, the one on the rooftop, okay, disappear. Okay. So remember, the edge detector usually comes after the smoothing filter. Okay. Okay. And this is the 45-degree line. Okay, the 45-degree line. Yeah, you can try this easily, okay, using the edge detector, okay. Next is Laplacians, okay. Like I said, there are two Laplacians. The one in the middle is 4 and the one when the middle is 8, okay. If it's the one in the middle, the pixel in the middle is 4, it's going to be -1 in the northeast, southwest. If the pixel in the middle is 8, it's going to be -1 all around. Okay, we use this formula. Laplacian of f is Laplacian of f by the derivative of f with respect to x squared, and then plus the second derivative of f with respect to y squared. Okay. Next, you can see, we just told you, right? We just learned that the second derivative can be very sensitive to noise. Okay, so before we finding the second derivative, usually we'll have to get rid of the noise first. Okay, and what's the best way to get rid of the noise? It could be the Gaussians. Okay, so you apply Gaussian first, and then apply the Laplacian next. And people just have, somebody just come up with Laplacian of Gaussians. Okay, log stand for Laplacian of Gaussians. Basically, it's just taking the Laplacians of the Gaussian function. Okay, and this is the function, the Laplacian of Gaussian function. It looks like this. Okay, so this is the Gaussian, right? Is this the Gaussian? Okay, you pass through the Gaussian and then you take the derivative of the Laplacian. Okay, take the second derivative of the Gaussians. Okay, so this is the equation for the Laplacian of Gaussians. Since it's the second derivative, we usually follow by zero causing. Okay, and then followed by the tertiary. So this is the image, okay? This is the log filter or the Laplacian of Gaussians. You can see it looks like the Mexican hat, okay? Sometimes people call it the Mexican hat filter, okay? And this is the 5x5, the smallest is the 5x5, okay? Not the 3x3, okay? And then you can extend, okay, to what? 7x7, 9x9, and so on, okay? So this is the filter, the log filter. Go ahead and do this, apply to peppers.
What is question mark?
Yeah, what is question mark? I'm not sure. I didn't finish it. You apply the filter and then you intro, right? Intro the I and the J. This is the log filter, Laplacian of Gaussians. First, you upload the peppers.png, change it into grayscale, and then change it into doubles, and then you filter it with the log filter. And then you intro. Okay? Go ahead and do that.